Okay, this may be a little off the cuff, so don't expect too much, but I just wanted to give you a couple examples by which you can do your homework. My pen works? Okay, ready to go. So, in the previous lecture, I introduced Ohm's law. The voltage equals the current times the resistance. The current is proportional to the voltage is another way of stating that, and this is the proportionality constant. So introduced Kirchhoff's law. Talked a bit about what that means. Both of Kirchhoff's laws, sometimes called the point law, one involving current, one involving voltage. These are the equations that you will need in 1705. Other than that, you just need some sort of working knowledge about what a capacitor does and what a you really don't even need to know what an inductor does, but you need to know what a diode does as well. But as far as calculations go, these are probably the only ones that you are going to use. So let's start out with a very simple example. Here we have a voltage source right there and a resistor. The voltage source supplies 10 volts. And let's say that we want to know what the current I1 is going through that circuit. So some current is going around in circles there just because we have this voltage source which kind of acts like a pump, and with the hydraulic analogy that we talked about, then the current is kind of like the flow rate of the water. So the electrons just move around and around this. Well, we talked about that too, where in electrical engineering or circuits, we I'll keep it. We talk about the current being positive when the electrons are going the opposite direction, but don't let that get you confused. Let's just focus on the equation here. Keep there. Hopefully that doesn't come up. So where was I? Let's start with Kirchhoff's second law. So we want to sum up the voltages as we go around the circuit, the change in voltages. And we know this one here, it's a positive 10 volts. So this pumps the voltage up 10 volts. Then it drops here as it goes over the resistor. Let's call that V1. And that's all we have. So really the change in voltage over this component minus the change in voltage over this component has to equal 0. I say minus, whereas Kirchhoff's law is a summation because this is voltage drop, so that's really negative. So V0 minus V1 has to equal 0. With that, we can easily tell that V0 must equal V1. So this voltage here is equal to V0, which equals 10 volts. Using Ohm's law, V equals current times the resistance. We know this now. We know this, that's given. So it should be easy to find this. We just divide both sides by R1. So the current equals V1 or R1, 1, which equals 10 volts over 30,000 ohms. So 30 kilo ohms, 30,000 ohms. So equals 1 over 3,000 ohms, which is 1 over 3,000 amps. It's really 1 over a third milliamp is a nicer way of putting it. So that is that. Let's try something a little bit more complicated. Here we've got the same resistor, same voltage source, but we've added a second resistor in line. So let's say that we've got a voltage drop here of V1, voltage drop here of V2. Say we have a current going through this resistor of I1, current going through here of I2. Now, if you go to your intuition of what would happen if this was a pump here and then these were just, like this were large pipes and these were two very narrow pipes, you should come to the conclusion that these two currents should be the same. I1 should equal I2. If you use Kirchhoff's first law, you could say that I1 is coming into this point whereas I2 is coming out, going through this resistor, and what goes in has to equal what comes out. So let's just call that I. Now let's use Kirchhoff's second law and look at the voltages as we go around. We should have V naught, that gain in voltage right there of 10 volts, minus the voltage drop over resistor 1 minus the voltage drop over resistor 2 has to equal 0. Use Ohm's law, so V equals IR. We know that, let's rearrange that, so we have V naught equals V1 plus V2. Using Ohm's law, that's IR1 plus IR2. Remember, because these two currents are the same, so we can take that current outside of the parentheses and say R1 plus R2 equals V naught. So let's go over here. We know R1 and R2. We want to know the current. We know V naught is 10 volts, so we can say the current equals 10 volts divided by 30 plus 10 kilo ohms, which equals basically a quarter of a milliamp. Just on a quick side note, so here we have two resistors in what we call in series. There's one right after the other. Just in general, if you've got a voltage source, you got resistor 1, 2, 3, 4, like that. R1, R2, R3, doesn't matter how many you have, let's say Rn. You can treat this whole system as if it was your voltage source with, let's call it R0, where R0 equals R1 plus R2 plus R3 plus R4 in this case, just equals the summation of all the resistors. So keep that in mind if you have two resistors. We're also going to talk about how you can use this to get a voltage divider here. So let's go back and do that. So let's say that we wanted to know what the voltage is there. Let's call that, let's just call that V1. Oh no, we've already called that V1. Let's call that no, not infinity. It's really the voltage drop over V2. So let's call that, it is V2, because here we know the voltage equals 0, because, essentially whenever we draw that, we assume that there's a ground there. So V2 has got to equal the voltage right here. So how are we going to find that? We found the current. We know the resistance. So V equals IR, where R is 10 kilo ohms, and I is 1 over 4,000 amps. So 10,000 divided by 4,000 is going to be 2.5 volts. So we know the voltage at this point right here is equal to 2.5 volts. So if we wanted to change this and alter the voltage that we have here and use that voltage for something else, and this is something that you're going to be doing in your homework, use that voltage, you might want to use it to power an LED or something like that, or in your case power the spectrophotometer. You just have to toy with these resistances, these R1 and R2. Okay, moving on. So let's take a look at what happens when instead of having the resistors in series, we have them in parallel. So here we've got our voltage source, 10 volts, still the same, R1 the same, R2 the same. Let's start with Kirchhoff's second law. So we just follow a loop around. Let's change my pen color. So we have two loops that we can go around here. We can go around the blue one in the center there, or we can go around the red one. And look at the change in voltage as we go around each. So here we've got a voltage gain of 10 volts and a voltage drop, V1. Voltage drop here of V2. So we end up with two equations because we can do two loops around the circuit. So first one would be V0 minus V1 has to equal 0. The second one would be, because in that second loop, the only thing that exists is the voltage source, and the second resistor would be V0 minus V2 equals 0. Now for both these equations to be true, the only way that can be is if V1 equals V2, right? So let's just call that V. But we do have an issue up here where we've got, let's call that I0, and then we have I2 going through the second resistor, and then we have I1 going through the first resistor. Well, we can go back to Ohm's law, so we know, V equals IR. For the first resistor, we know V, which is just this voltage here. It's the 10 volts. So that has to equal 10 volts. So yeah, equals V0 equals 10 volts. So V equals I1 R1. V also equals I2 R2. And we know that from Kirchhoff's first law, if we look at what goes into and out of this node, we know that I0 has to equal I1 plus I2. Just a moment.
Okay, we're back. I got a little tired, but and as I was tired, let's start where we left off. But I forgot to mention, I said we could have two loops. We could actually have three. So we could go around this loop here. So say we went that direction. So the voltage increased as we went from this point, which is 0 volts to this point. It's got to equal the voltage decrease as we go from this point to this point. So yeah, so in that same way, we would know that V1 must equal V2 must equal V0, which equals 10 volts as we have as a given. So let's see, we have three equations. 1, 2, 3, three unknowns. I1, I2, and I0. And we want to determine all those currents in this circuit. So we fully define the circuit. Let's move down here, we're running out of room. So, pretty simple, right? We know the voltage, we know the resistance. So we can calculate I1 and I2 pretty easily. I1 has got to equal the voltage, 10 volts over R1, which equals 10 volts over 30 kiloohms, which equals, just as it was in the third problem, 1/3 of a milliamp. Do the same for I2. I2 equals, let's see, voltage divided by 10 kiloohms this time, which equals 1 milliamp. So, as is plain to see, I1 is less than I2. The resistance going through this leg is greater than the resistance going through this leg. So if we were to think about this again in terms of water in pipes, this is our pump. These are two constrictions in the pipes. This one's more constricted. So of course, more of the water is going to flow through this pipe than is through this pipe. At this point we know that I1 equals a third milliamp, and I2 equals 1 milliamp. So what does I3 equal? Well, because conservation of mass, conservation of charge, electrons don't just disappear, I naught should equal I1 plus I2, which is simply I naught equals 1 plus I2 equals 1/3 milliamp. Excellent. We now know all we need to know about this circuit. Okay, let's take a look at how you would, just in general, look at resistors in parallel. So we just did 2 in that case, but what if we had another one? What if we had resistor here, and on and on. Let's that's R1, R2, R3, R4, all the way up to Rn. What would be an equivalent circuit? So if we wanted to simplify this, just say that's equal to a circuit that looks like this. We've got the same voltage source. In this case, we've got R naught. We want to know what R naught would equal. Well, we just calculated the current, right? That was our I naught in that last example. And we know through Ohm's law that V equals I R. So it's the same for that. We know that R naught is got to equal V naught over I naught. So what is I naught? We know the voltage drop across these all have to be the same because they're in parallel. So we can calculate the current across all those, and then when we sum them up, they've all got to equal I naught. So I3, I4, I1, I2, all those added up have got to equal I naught. So we know, I1 equals V naught divided by R1, and that just goes on and on. So, in general, I naught is going to equal I1 plus I2 plus V3, so it's V naught divided by R1 plus V naught divided by R2, and on, so we got V naught divided by Rn, where n would be 4 in the case I've drawn here. So we can take the V naught out of there, and we get V naught times the summation from I equal 1 to n, 1 over Ri. So go back to Ohm's law. That resistor, that R naught, it's got to equal V naught over I naught. In this case, we've got V naught on top, and we plug in I naught, we got V naught again. That summation I equals 1 to n of Ri, or 1 over Ri, either one, erase the power there. So those V naughts cancel. That hurts. And we get 1 over summation I equal 1 to n of 1 over R. So I. So in general, when you have resistors in parallel, you can collapse them all down into one resistor using an equation like this. You might end up having, a circuit that has resistors in series, and maybe some in parallel too. So you could collapse, these two together, collapse these together, and then eventually collapse them all together into one equivalent circuit. But you're probably not going to need to do a lot of that in this class. We will encounter it later, I bet, because it's, if you haven't already taken it. Okay, next problem. So I just, I said you're not going to really need to know the equations that govern capacitors, but there is one in your homework, and I just wanted to make sure that you understand what qualitatively happens with a capacitor. So remember, with the hydraulic analogy, if this was, a pump, and this was constriction in a pipe, with the hydraulic analogy, we look at a capacitor like a container that has a rubber, like flexible diaphragm in there, so it can flow into one side of the container and flow out, but no fluid ever makes it through that diaphragm. Just that diaphragm can flex. So if we add pressure, which is a lot like voltage in the hydraulic analogy, so if we if we add a great pressure there, then this diaphragm is going to bulge out, right? That's P1 is greater than P0. Or in this case, where it's just flat, P1 is going to equal P0. So let's consider what happens right when we turn the circuit on. So when we turn it on, we introduce pressure here where it used to be a pressure of 0. So it used to be this case. All of a sudden, P1 jumps up. As P1 jumps up, it begins to flex this diaphragm. So we do get a little flow of current or water in the hydraulic analogy into here at time equals 0. A little flow here. But eventually, because no liquid, no electrons are going to ever make it past this barrier, it's got to go to 0. So what it looks like is, if you look at the curve. Okay, let's, I'm going to do this a little bit differently than the way I was going to do it. So let's start with the equations, actually. Even though I said you're not going to use these, to calculate values, I want you to understand them qualitatively, so what happens on a gut level with the capacitors and inductors. So I gave you these equations in the last lecture. I'm just going to show you how they are used here. So if we want to know that current, we know the current through a capacitor is equal to the capacitance times the derivative dV dt of that voltage across the capacitor, where the voltage is a function of time. So let's take a look at what happens right here when we turn on the power. So basically, we start at 0, and at time equals 0, we turn it on to 10 volts. It's time equals 0 right there. So that's what we call a step change. So suddenly, there's a voltage difference across here. And if we have a step where we go from 0 to 10 in 0 seconds, basically, so this is all idealized, this is infinite, right? So in that instance, this capacitor acts as though it's not even there. So like if this was a hydraulic system and we turned on a pump, this diaphragm isn't stretched at all, so the first little bit of water can push on it as though it's not even there and move into this chamber and push out liquid from this chamber, and it's as though this is just a pipe. But as time goes on, this diaphragm is not going to stretch infinitely. It's going to keep pushing back more and more as the pressure builds up in here, but it's never going to let liquid flow through. So intuitively, we know, if we look at current versus time, that at time equals 0, then that current has got to be some positive value, and it's determined by that resistance. And we've already done that problem. That was the first problem we did. So it starts at that resistance, and we know at time equal infinity that that capacitor is not going to let any current through. So it's as though, oh, yeah, it's as though there's a break here. And that line is not there. So this would be time equal infinity, and this one would be time equal 0. So it would eventually asymptotically go down to 0, and the speed at which it goes down to 0 would depend upon that resistance, that R1, and capacitance at C2 here. So 0. That's what you'd need to know about capacitors. That T equals 0. The current through them would be infinite if it wasn't for that resistor, but in this case it equals IR, and at T equal infinity, current equals 0. Steady state is when T equals infinity in this case. So let's take a look at the case where we have an inductor in there. So remember the hydraulic analogy for the inductor is water wheel. I have a hard time drawing beautiful water wheels, but there is our water wheel. So at time equals 0, again, we've got our voltage time, we have our step change, a little slanted there. But that first little bit of water that hits that, it hits across the face of that water wheel, and all the energy goes into starting the motion of the water wheel. Now when this thing is going for a long time, in steady state, time equals infinity, this thing is whirring right along with the water. It's as though it's not even there. Same thing happens with electrical current. So time equals 0, and I'm trying to push electrons, well, let's not get into which way the electrons are flowing, but in this case where this is positive voltage, they'd be flowing this way. Time equals 0, all the energy goes into building up the magnetic field in the inductor here. So it's as though at time equals 0 that there is a break in the circuit. And we can see that in the equation for the inductor. So cross that out. The current across an inductor is 1 over the inductance integral from 0 to t of the voltage, which is a function of time, dt. So, at time equals 0, there's a step in the voltage there, but not very. If we take a very thin slice in here, it's very small. But as time goes on, we take greater and greater slices, integrals, which are the area underneath that curve. So we know at time equals 0, I must equal 0. And we know at time equal infinity, it's as though this is just a wire. The water goes straight through. So the time current across the inductor at time equals 0, it's 0. No current gets through. The voltage just jumps up. But eventually it goes up to that IR, which is the resistance we calculated in the first problem. So time equals 0, crossing the inductor, current equals 0, time equals infinity, steady state current equals that I sub R, which would be infinite if it wasn't for the fact that we've got resistance. So that's it. That should be enough to do your homework. If not, send me an email, stop by my office. I look forward to seeing you in class shortly.